I want you to learn how to predict the charges of the main group elements using the octet rule. So we're going to start with the octet rule and try to understand what it's telling us when we're thinking about ionic compounds. And then we'll move into using that to predict charges. We're going to predict a trend, which is going to allow us to memorize less and know a lot. So the octet rule, just looking at its title, you may think octet, which is the number 8. So let's see how the number 8 plays into this rule. So it says the octet rule, elements will lose, gain, or share valence electrons to reach the electron configuration of the noble gas closest to them on the periodic table. So we're going to start with ionic bonding. So we're going to be thinking about the losing and gaining of valence electrons. Remember, valence electrons are the outermost electrons, and they're the ones that play a part in reactions and bonding. So we're going to think about losing and gaining, and then it mentions electron configuration of the noble gases. On the periodic table, the noble gases are in group 8A. They are the last group on the right on the periodic table. And all of the noble gases, except for helium, have 8 valence electrons. 8 valence electrons is the maximum. It means that both your outer S sublevel and P sublevel are full. So no matter what level the noble gases are on, except for helium, I'll mention that in a second, you have S2, P6 as your valence. Okay, and let me write that a little bit differently. So it would be in whatever level you're in, S2, and then in whatever number you're in, P6. And we'll look at some specific ones in a few slides. So they have a full valence, and that is very, very stable. Now, hydrogen, which is on the period 1, if you recall, and you can review electron configurations, energy level 1 only has a sublevel S. So on the first level, the maximum is 2 electrons. So helium can't go up to 8. It only can go up to 2 because it doesn't have any p orbitals. But for helium, that is completely full. So all of the noble gases, including helium, have full valence, but it's the ones from the second period down that have the 8. And that's where the octet comes in. Having 8 valence electrons is a very stable place for the representative or main group, the letter A elements, to be. So we're going to use the octet rule to help predict the ions formed by the elements in the main group. Now, before we go on to the prediction, I wanted you to connect the ions, if they're given to you, with the octet rule. So I'm going to again do letter A and show you what this is asking you to think about. And then if you'd pause the video, you can finish out B and C. And then when you unpause, I'll answer your question. I'll give you the answers. So letter A is an oxide ion. And I'll mention that in just a second, why I'm calling it oxide. Before I leave this slide, I'll mention it. But I see that it's an oxygen, so oxygen is right here. And it has gained 2 electrons. And I know that because it has a 2 negative charge, and negative charge comes from gaining electrons. So oxygen with 8 electrons, if it gains 2, then it would have the same as neon, because it would also have 10 electrons. So the noble gas that would have the same electron configuration as the oxide is neon. Now, oxygen is not becoming neon by gaining its electrons because the identity of an atom is determined by its number of protons. So oxygen is not changing that it has 8 protons. What it's changing is that it has now 10 electrons. So I kind of think of it like it's dressing up, like it's putting on the outfit of neon. What we see on the outside, the valence electrons of oxygen, looks the same as what we see on the outside of the neon. So I want you to go ahead and answer B and C, and then I'll come back and I will answer those questions and then tell you why I called O2 negative oxide. So pause the video and try to answer B and C. Okay, so let's do magnesium. So I find magnesium, which is here, number 12. Now magnesium ion is Mg2+, with a 2+ means it has lost 2 electrons. So magnesium starts with 12 electrons. If it loses 2, it would go back to neon. So both the oxide ion and the magnesium ion have the same electron configuration of neon. There is a word that is used when elements and ions have the same electron configuration, and it's called isoelectronic. So when atoms or ions have the same electron configuration, we can say that they are iso, meaning same, electronic. So the same electron configuration. All right, so let's look at the bromide ion. It's kind of hard to see, but there is a -1 charge there. Sometimes that doesn't raise up high enough on the font. But bromine is number 35 here. If the bromine has a -1 charge, it means it's gained 1 electron. So bromine would now have 36 electrons like krypton. So you can see, or you can start to understand when we say that atoms will gain or lose to have an electron configuration like the noble gas closest to them. Sometimes it helps to look at the periodic table and then reflect on, oh, if I add 2 electrons, I get to neon. If I take away, I get back to neon. Or we can imagine or see using the periodic table what that octet rule is telling us. Now, before I leave this slide, I want to mention to you some of the naming, and I'm going to try to call things their correct names. We'll learn naming more in a different chapter. So anions are named by changing the end of their of the element name to IDE. So for example, O2 negative is called oxide ion. So instead of oxygen ion, they call it oxide. So they use some part of the beginning. Sometimes they call it the stem But what's hard about that is it varies. So some of this just comes with practice, and that's why I would like to start using the correct names of the ions, even though we have not officially gone over the rules. So let's start thinking about them that way. So the anions, the ending of their element name will change to IDE. So in this case, O2 negative is oxide, and Br negative, instead of bromine, it would be a bromide ion. So for anions, the name changes from the element name. Cations, they're named the same as the element. So I have one example here, which is magnesium. So Mg2 plus would just be called the magnesium ion. So I'm going to start calling them by their correct names, but this is what I'm using as their naming. All right, so let's look at electron configurations, and I want us to get a pattern. So what I've done is I've taken two metals, and on the next slide I'll take two nonmetals. I've written their electron configuration and the electron configuration of the noble gas closest to them. And so I want us to see a pattern, and then we're going to take that pattern and apply it to the periodic table. And on the introduction of this video, I mentioned what I'm trying to do is have you understand more so you can memorize less. All right. So an important thing that can help you is remembering that metals form cations. So metals like to lose electrons. All right, so let's look at our examples. So I just picked one element from group 1A and one from group 2A. I'm in the third period with sodium. And so for group 1A, I wrote down the electron configuration for sodium. And group 1A's sodium's valence electron is this 3s1. The third level is the highest. It's in the third period. And so that's its valence electron. The noble gas closest to sodium on the periodic table is actually in the period before it, and that is neon. And so what I want you to see is if we remove that 3s1, I'm using my pen to take it away, then what you can see now, compare sodium to neon, and do you see how they have the same electron configuration? Let's do it again. So I'm taking 3s1 and I'm going to remove the 3s1. So I'm losing that valence electron. And so now when you compare the sodium electron configuration to the neon electron configuration, they're the same. This is what the octet rule predicts, because the noble gases have a full valence shell, which is stable, and so the other elements will gain or lose their electrons to have that. And so what sodium does is it loses one electron. Now, losing one electron then would form a positive 1 charge, and so the ion is Na+. Now, fortunately, we don't have to write electron configurations every time we want to predict this. What we know is that every atom in group 1A has one valence electron. And what we can then predict is every atom in group 1A will lose that one valence electron to form a positive 1 charge. So what we understand is just a piece of it. But then we can predict that all of group 1A will form a +1 charge. And I'm going to fill in, so I have a periodic table here. And so on this, I'm going to write the charges predicted from the octet rule. So group 1A, I'm just going to write a 1 plus on the top of it. I'll put a 1 like this so we know. So that's what I predict. So I'm not going to memorize the charge of potassium. If I need to know the charge of potassium, I'm going to come to my periodic table, find potassium in group 1A, and know that that has a 1 plus charge. Now let's go back and get our pattern. All right, so now I just, on this page, again, I'm not doing this so that you have to memorize everything. I want you to see how it's all connected. So on group 2A, I chose magnesium, which is just one more element past sodium. So we look at its valence electrons, and it's still in the third period, so it's still, whoops, let's hope I can go backwards. There we go, sorry. I was like, oh no, it's like class. Okay, so here it is, 3s2. That's its valence electron. Okay, so we just added one more. Now let's just imagine again, and I know for some of you it's easier to imagine than others, but if I take away the 3s2, so take away the valence electrons, now compare magnesium to the noble gas closest to it, which is neon, and you'll see that they match. Okay, I'm going to do it again. So there's the 3s2, and I get rid of those 2 electrons. And now the electron configuration for magnesium and neon match. This is what the octet rule is saying. So it says what magnesium would like to do is lose these 2 electrons. And that way it will have the same electron configuration of the noble gas closest to it, neon. And when it loses the 2 electrons, it becomes magnesium with a 2 plus charge. We would call that the magnesium ion. Remember, metals, their cations are named the same as their element. So let's put this on the periodic table, because what we know is every element in group 2A has 2 valence electrons. And so if any of them lose those 2, they will go to the noble gas closest to them on the periodic table. So what I predict, or what the octet rule predicts and what I learn, is that group 2A has a 2 positive charge. So again, I'm going to learn the pattern and not memorize all the elements. So then if I'm asked, or I need to know, what's the charge of a barium ion? Then I find barium on the periodic table and I say, oh, it's in group 2A, so barium forms a 2 plus cation. So those are 2 examples of metals that are forming cations. Now we're going to look at some nonmetals, and then we'll fill in our pattern. So here's the nonmetals, and I'm going to highlight this because for me, this is something that helps me not make mistakes, and kind of it's one of that basic kind of information that can often steer me in the right direction. So nonmetals, which are on the right-hand side of the periodic table, form anions, which means they gain electrons. So if we look, I now just chose randomly, and these are from period 2. I chose oxygen from group 6A and the halogen fluorine from group 7A. So the noble gas closest to both of these elements is also neon. Okay, so that's because it's just past them on the periodic table. So when I compare their valence electrons, what I notice in oxygen is it has 2s2, 2p4. There's at 6. And if you compare that to neon, you'll see that it's missing 2. So what happens is, if this number, I will substitute it. If I take away the 4, and I add 2 more and I make it 6, then they would have matching. So in this case, it's not about losing anything, it is about gaining. And so oxygen will gain 2 electrons, so it has the same electron configuration as neon, and it becomes O2 negative. And remember, the negative ions, you change the ending of the element name to ide, I-D-E. So that's the oxide ion. Now then, what I can predict is the elements in group 6A all have 6 valence electrons, and so to get to 8, they will add 2. So then on this periodic table here, I am going to predict that group 6A would form a 2 negative charge. So let's do the halogens. Let's do fluorine. So fluorine, you can see it has 7 valence electrons. Its valence shell is 2s2, 2p5. And so to get to the 6, it's going to gain 1 electron. And so if it gains 1 electron, it becomes F, and we don't write the 1s when we're writing the ions. It will just get a negative charge if it's an anion, positive charge if it's a cation. So I'll just write a negative. And this would be called fluoride, because we're changing the ending to IDE. And so what I can predict in the big picture is the halogens in group 7A will form a 1 negative. Now I am writing a 1 on my little prediction chart here just to keep me straight. All right, so let's fill out what we know, and then we're going to try to use this information to see if we're at a point where we can start putting together ions. So what I can tell you is the noble gases are not going to have a predicted charge because they all have a full valence, so the octet rule would predict that they won't form anions and cations. Now, the other thing the octet rule does not predict is for the transition metals. So I'm just going to write here, ions cannot be predicted for, I'm just going to write T, transition metals. So the octet rule will not allow us to predict these here. Okay, so we're really just talking about the representative elements, so everything with an A. So if we continue on and we go to 3A, these have 3 valence electrons, and so it would still be closer to lose the 3 valence electrons that they have. So these form a 3+. I want to skip 4 for a moment. And then 5A, go to 5. 5 now is getting they're non-metals. They're getting closer. Well, there's a mixture, but they're getting closer to the halogens that are past them. And so now this is where they start gaining. And so that leaves group 4A. And some tables that predict, they actually just leave this one blank. I, in my patterns, don't like things I have to skip. So as I process through it, if you have 4 valence electrons, you would have 2 choices. You could lose 4 or you could gain 4. So in the octet rule, you could see you could have 4 positive or you could possibly have 4 negative. Because you could gain 4. And then you might think, well, why would some be positive and some be negative? Then I fall back on the idea that positive ions are formed by metals and negative ions are formed by nonmetals. So in this group here, any metal I would think would be a 4 plus and nonmetals would be a 4 minus. Now here's why a lot of people leave it blank. There aren't 4 minuses in group 4A. Carbon and silicon, if you remember from trends, are at the top of the periodic table. They're small atoms, and it's hard. The 4 negative charge is too much for their stability. So even though the octet rule might predict it, we won't encounter it. So it's not really something I'm going to have to worry about because I'm not going to encounter it in the work that I'm doing right now, because it's not going to happen. 4 positive is a possibility. We will see it in a different chapter. I don't think we see it too much in this discussion. But both lead and tin are large enough to handle a 4 positive. So I know for a lot of people to say, well, we're not going to see it, but this is what we'd predict, feels unnerving. But that's sometimes how it is. So we have this nice pattern. I like the pattern. I'm going to leave the 4s there. I am not going to worry about the 4s too much. We will start incorporating the 4s and tin and lead as we encounter them. But the other ones we're really not going to encounter. And so I'm not going to worry about it. But I do like the pattern. So, big picture. You need to understand the octet rule. You need to understand what it means when it says they'll lose or gain to have the same electron configuration. So conceptually, you need to understand that. Practically, when we're working and a lot of the things that we do, you need to be able to predict the charges of the representative elements. And to do that, you need to learn, memorize, reason the charges that we predict for each group. So that when you're given an element, which I have a slide to try this, you're given an element, you can use the periodic table to predict the ion that element would form. So on the next slide, here's some practice. Now I'm going to go ahead on this little periodic table. You hopefully were writing down the pattern for you to use in your own work and homework from the previous slide. But I'm going to write it on this periodic table. Now I'm going to show you what we're going to do. I'll do one, pause it, you try to do the others, and then see if you're understanding. I am also going to name these ions because we're just going to start practicing that. Okay, so I'm going to do letter A, then you can pause it. So calcium, what I would do is I would find calcium on my periodic table. I would see it was in group 2A, and so I know the charge is a 2 plus. So the ion is calcium 2 plus. And then this is names just as a side. This is called a calcium ion because cations are named the same. All right, so pause. You try to answer B through E, And then you can restart it again, and I will go through the remainder of these B through E. All right, so selenium is letter B. So there's selenium over here. It's in group 6A. So selenium, I predict a 2 negative charge. Negative, the ending changes to IDE, selenide. Oops, sorry, nide. It's a weird one. Selenium turns to selenide. I don't know if anyone says saline. There's probably other ways to say it. I say selenide. Okay, potassium, K, is right here. It's in group 1A, so it's a plus. We don't write a 1, we just put plus. And so that's just called the potassium ion. Letter D, bromine. So bromine's here. It's a halogen. It's a negative 1. It's called bromide because the negative one's the ion ending changes. And then finally aluminum, which is right here, is in 3A. It's a 3 plus. Called the aluminum ion. All right, so our next thing is going to be putting ions together to write the formulas for compounds. So you're going to need to be able to do what we just did on this page. So I would recommend before you watch the video on ionic compounds that you have a periodic table that's labeled with the charges so that as you can follow along as we work on that next thing.